Hey everyone, thank you guys can hear me, but let me know if not. Yeah. Good. Share my screen. Just share my whole screen. That would be easier. Okay, cool. Can you see that? Yeah. Okay. So just to go over some basics on Gaussian processes and introduce some notation that would be useful to have in mind when talking about the rest of this paper. We're looking at return Gaussian processes on graphs, but they're not usually defined on graphs. Usually you have data, which is real valued data. Don't need that screen, I don't think. Real valued data. And lots of machine learning tasks can be done via nonlinear high-dimensional interpolation of possibly noisy data. Some tasks can be done like this, such as regression. This is an example of regression, and classification, when the output is not a real number, but it's an integer or a class. And it can be done with neural networks. And so nonlinear regression with neural networks should be kind of familiar. The simplest example, the very simplest, most basic example, is a multi-layer perceptron with one hidden layer and some nonlinear activation function. And with or without regulation, you can get something that looks like this when you train it. But can we solve these tasks with Gaussian distributions? Why would you want to use a Gaussian distribution? A Gaussian process is a random function with error bars that can be used to quantify uncertainty. And yeah, that's really one of its key properties, is its ability to produce not just a mean prediction, but also a set of error bars that can be used for uncertainty quantification. So the definition of Gaussian process is a random function, f from a set x to the real numbers, such that for any set of evaluation locations, the value of the Gaussian process at those locations is a multivariate Gaussian. And as a consequence, every Gaussian process is characterized by a mean function and a covariance kernel, K. And it's really the covariance kernel K, which is the meat of the Gaussian process, because it allows you to condition on data points that you have and then ask questions such as what's the mean and uncertainty error bar around a new data point that you don't have. And you want to make a prediction for. And so you define a model which is completely or almost completely characterized by the covariance kernel. And that's a prior over functions. For example, you could have some smooth function that if you change your input by a little bit, then you don't expect your output to change by a small amount. And this function would apply smoothly over your data. This is a Matern kernel, and this is in a particular case of a Matern kernel with some parameter set to infinity. So it's infinitely differentiable, infinitely smooth. A GP posterior is directly computable, which is another advantage of Gaussian processes. It's completely analytically tractable. You can get it in one step by inverting this kernel matrix K. And that's how you train it. And so we employ Bayesian learning by conditioning on the data points that you have in your training set, and then you can test on any data point along the x-axis here, but have one or more input dimensions, and you could have different priors over functions that would be less smooth than this, for example. But the key point is you get an error bar as well.
Can I ask a question?
Sure.
Maybe basic example. How important is it to get the inverse matrix accurate? Can it be approximate?
It can be approximate, and there are good reasons why you'd approximate it, because it's really slow to evaluate if you have over, say, 10,000 data points. It's also like memory intensive.
Does it affect the performance?
It would affect performance, yeah. And there are some approximations where you could expect to get like better performance by approximating in a certain way with like inducing variables, but that's the whole literature which is dedicated to approximating k to the -1 with something that, so this k to the -1 thing, it's got a computational complexity which is order n cubed, where n is the number of data points, and there's a whole literature dedicating that complexity to order n squared, where m is some number of inducing variables, and so it's only squared in the number of data points.
Maybe make it specialized for your specific application, like induce sparsity or use low rank probabilities that will make this stuff like that.
Yeah, exactly. Yeah. Thanks.
K is the covariance matrix that's defined by the training set.
Yeah.
And Y is the labels for your training set.
Yeah.
But then you calculate this other vector, which is X star X, and that's how you evaluate on your points.
Yeah, exactly. Yeah. So this is the key point. This is a covariance kernel, and the amazing thing about it is that for a new point, you can evaluate predictions as long as you've got that inverse of the training data. And this is why we work with K instead of K to the -1, because if we were to invert, to write, say, Q is K to the -1 and then write everything in terms of Q, you'd get like a Q to the -1 here, but that wouldn't compute, because if you had another input point, then everything in that precision matrix would change. But the nice thing about covariance matrices is that if you add a point to a covariance kernel, then it doesn't change the other elements. You just add a new row and a new column. And that's a property of covariance functions as opposed to the inverse of a covariance function.
Does Y have to be a single number?
Covariance functions kind of measure correlation. And if you had like a sparse model, then the edges of like a sparse graph would be values that take on values in the precision matrix, which is K to the -1. And it's kind of analogous to like a graph of Gaussian, this K to the -1, if you had a sparse model.
The inverse with the Laplacian of K.
The inverse, yeah.
Inverse.
Yeah. So that if you had a graph, if you add a new point, then K would change drastically, but K to the -1, it's more stable. It's still sparse. It's still got loads of zeros. Yeah. You just add some weights, and the graph of Gaussian is defined in terms of a weight matrix and a diagonal matrix. Which is the adjacency matrix. Yeah, which could either be weighted or unweighted, ones or zeros, or with normal ones or zeros. That they give in the paper, where a Gaussian process wouldn't cut it. It wouldn't be a good prior model. But there is some sparse, there's a structure in the data that we need to exploit if we're going to make good predictions. Here on the GPS, so this is like a coordinate of a GPS. This is another coordinate, so north, south, east, west. The traffic speed along the roads doesn't vary smoothly with the GPS coordinate, because on one side of the road, it could be very quick. On the other side of the road, so that's orange colored. On the other side of the road, the traffic speed is very slow. So it wouldn't be a good data set to have having X as the coordinates of the GPS and defining a return Gaussian process prior over it, because what you'd get, this is a sample from the prior, is that this function, the traffic speed, would vary smoothly, and along different sides of the streets, you'd get approximately the same traffic speed, which is not a realistic assumption to make. So when you make a prior, making some assumptions about the data set, this is not a good assumption to make. So it would be a bad choice because the traffic flow is unlikely to depend smoothly on the GPS coordinates. So the idea in this paper is that you can apply, if you know you have this kind of example where you have a graph which has vertices, which is where we measure the traffic flow, and edges, which are the roads. And say we put the weights of the edges as the inverse distance between the measurement locations of the traffic speed. Then the data is a graph. And then we've got the labels Y, which is the traffic speed, on the measurement locations. And for this graph, we can have a prior, which is a Matern Gaussian process graph prior. And this turns out to be quite performant. Or the idea is that it's going to be much better performing, at least, than the Gaussian process prior, where you use the GPS. But it's no silver bullet. So some questions I have after reading this paper, which we'll get to, is like, what's an appropriate way to deal with the weights on the weighted graph? Who said that the weights should be an inverse distance between the measurement locations, right? The distance between this part of the road and somewhere down the street. Who said that that's what the weights of the graph should be? Yeah, the paper doesn't give a suggestion of what weights we should assign to the adjacency matrix.
Think about it. So they put inverse the distance between points as weight.
Yeah. So the idea is that the weight would be large if the distance between measurement locations is small.
Right.
And so therefore there will be a strong relationship between nearby measurement locations. Yeah, it makes sense.
Actually, it is in the thing with our graph. If the two nodes are closer, you want them to be more correlated, which is not the higher weight.
Yeah, but who says it's going to be an inverse relationship? What about inverse square?
Yeah.
That kind of thing.
Well, it's kind of like.
Yeah.
I remember experimenting with those big like long squares and one node. Well,
you end up just picking something that performs well on like a test set, for example.
Yeah.
But since this is a theoretical paper, we want something better than that. I want them to tell us like what do you expect given some maths is going to perform well. And they do suggest that if you have some weights, then the graph Matern Gaussian process kernel converges to a Matern Gaussian process kernel. But that's only for some specification of those weights. Like they've defined the weights.
So they define the weights to make
to make the maths work, to make it converge. And it's a weird thing though, because if you've got a graph, then you don't have distances, like you don't have a vector space. There's no distances, but those weights depend on distances in the vector space. And so does it really converge to a Gaussian process Matern? Kappa naught. So what was the question? Sorry. I see. I think because, right, this is a good question. This is a good question because we define in a Gaussian process the kappa, which is a length scale here. Right here, which controls how wiggly the function is. And if I make kappa larger, then the function gets less wiggly because it's varying over a longer length scale. If I make it smaller, and it goes really wiggly. Smaller length scale. The question is, could I make the length scale kappa depend on the distance between nodes? Is this the question?
No, make it node dependent. Well, pairwise node dependent. Because you need to take into account both nodes.
Yeah. Yeah. Because there's only like a distance between two nodes. Mm-hmm. Yeah. And in fact, if you're talking about a Laplacian or a precision matrix, then we're talking about nodes and connections between nodes. But this is not that. this is a covariance matrix. So the length scale is something that is a result of some like assumptions you make on the weights between the nodes, but the length scale is not directly dependent on that. It's a result of that. When you invert that precision or Laplacian, then you get covariance. And so the relationship between kappa, which is defined in the covariance function, is not so clear as to the relationship of weights in precision or Laplacian graph matrices. Because this is not a Laplacian matrix, this is a covariance matrix, which is like the inverse of a Laplacian or precision matrix. So the relationship is not so clear. I can say, like, if you had some weights and you increased the weights, it would be like increasing the stiffness. And so I think in some sense, like the length scale would increase because if you increase like the stiffness of this bendy function, then it wiggles less. But that's the kind of intuition I have. So back to this example, back to the comments I had on the paper. Yes, so the Matern kernel operates in a vector space, but the Matern graph kernel is a function on vertices of a graph. Are there some important properties of the Matern kernel that don't mirror across to the Matern graph kernel? And if I add a new node in the graph, how easy is it to make predictions on that new node? And because we're defining precision matrices to define the Matern graph kernel, if I add a new node, then everything else in the inverse of the precision matrix changes. And so it's not easy. It's not easy to add a new node. In fact, you have to define a graph before you make predictions. And you can't add new nodes to that graph. Otherwise, you have to start over.
How does the... So you have one of the points to make, like the only way this is useful is if you have a partially labeled graph.
Yeah.
And so how do you incorporate the additional, like basically all the test points into the covariance matrix? Is it ignored during training essentially?
You have the test points. You have the nodes and the edges, but you don't have the labels, and it's the labels you're trying to predict. But yeah, you would need to have the test points, the input points.
But are the unlabeled point? I'm saying, like, if you, when you're training the graph, or you're training the Gaussian process, do you use those unlabeled points to determine like the hyperparameters of your?
Yeah, good question. I think not. I think they're just used for training.
And then wouldn't that mean that you're ignoring those edges and nodes in the covariance matrix that you're defining for training? Yeah,
I think so. Yeah, we should look at the examples to see how to get around that. Okay. I think that might be something that could break things. And how does it scale with a graph that's not sparse? If it's not sparse, then we can't use sparse techniques to invert this precision matrix to get a covariance matrix. So how does it scale? So how are we doing for time? Okay, cool. So this is a child paper to Matern Gaussian processes on Riemannian manifolds. A Riemannian manifold is, for example, like a sphere, something that's not like Euclidean space X, Y, Z, but on like a surface, curved surface. And it lays out some of the maths, except it replaces eigenvector and eigenvalue decompositions of the graph Laplacian with eigenfunctions and eigenvalue decompositions of some graphs. They are defined with vertices and edges, and those edges have weights. So completely defined through a weighted adjacency matrix, if you know what that is. See if I can get this full screen. Why would the space on which the GP acts matter? Arvid, could you like elaborate in what sense?
Okay. Can you hear me?
That matter to what, for example?
Can you hear me now?
Yeah, I can hear you. Yeah.
Okay. No, just intuitively, I'm not sure why.
I muted myself because. You should unmute your mic, your speaker, and then I'll mute mine.
Sure.
So you just want to. I think you have your sound on.
Can you hear me now?
Yeah. Oh, here we go.
Okay,
yeah. No, I was wondering, but what is like the intuition behind that? Why should a Gaussian process on a manifold be different from a Gaussian process in Euclidean space being different from Gaussian process on a graph? Is there some intuition of why we would expect something drastically different?
Because there's an example here. So there's a relationship between Gaussian processes and stochastic processes, stochastic differential equations. And so this is a function, and this is like a sample from a Gaussian process. If you generate some white noise process, and to solve for the Gaussian process, the wiggly thing from the prior, you need to invert this operator and bring it to the right-hand side. It's just like solving for x. Am I muted? No, I'm fine. But with the graph, that's not a function, it's a vector. And so instead of an operator here, you got a matrix which you invert. And so there are definitely analogies between the maths of vector spaces and function spaces, but they're not the same, and there's some differences. And I think the notion of a distance changes between like a Riemannian manifold and the Euclidean space. In the Euclidean space, you can go in one direction for infinity and your covariance would get smaller and smaller. But if you went one direction to infinity on a sphere, then the covariance is like periodic because it gets smaller and then it comes closer again, it gets larger. And that means you just went around the sphere once.
Yeah. You could argue in both cases you could just find a different space representation, right? Like a Fourier representation of what you wanna act.
Matter, I think. And
sorry, I think everything just stopped.
It's okay.
Never mind. It just.
Well, so my intuition for all of this is that like one of the fundamental ideas of the Gaussian process is that you use a distance metric to define points that are close to each other, and you use this, and like one of the ideas of the Gaussian process is you define a smoothness constraint where points close to each other should have similar ranges or values. And so you want your prior to encode distances that are meaningful. And so it, like Ben said, if you're operating on a sphere, then Euclidean distance could be like the wrong distance metric to use because 2 points that are actually 2 points that are close to each other should be the same. But I liked your explanation that like basically you could have 2 points that are really close to each other that depending on the direction in which you measure the distance, they'll be very far away on a sphere. Anyway, maybe that's a poor explanation. Let's continue.
One I think related point to what Peter was just saying is that if you try to the graph distance, you get something that is just not going to work. And the reason for that, so if you replace this distance, the norm of tau, which is the difference between 2 points, with a graph distance, which is like the number of nodes between the number of edges between two nodes, then it doesn't work because, and then there's some mathematical proof behind why it doesn't work. And it's because if you kind of define a graph on a manifold like a sphere, and you define the distance like that, like a distance between 2 points, 2 nodes, then it turns out to be a Euclidean kernel, which then doesn't make sense, because if you went infinite distance away, then in Euclidean space, then the kernel goes to 0, but it's not the same as a manifold where it doesn't necessarily go to 0. It might be periodic because you're going around the sphere. So it's things like that that matter, I think, when you go between different spaces. Yeah, so where should we go? So yeah, let's just look at this kernel in more detail. You've got a variance of the GP. Where do the targets, the outputs that you're trying to predict, how much do they vary in the data? Nu is the smoothness. So for that example that I showed with the wiggly functions, it was differentiable an infinite amount of times. And so it was very smooth, but if its nu is 1 or 2, then you can only differentiate it once or twice before it becomes a white noise process. Then kappa is the length scale, the scale over which the function varies. And so you want to tune those either by using cross-validation or by maximizing a marginal likelihood in the Bayesian setting to choose those parameters so that you perform well on the test set. And I guess the point at which this paper stemmed from was in 1963, when there was a guy called Whittle who made a connection between stochastic partial difference and Gaussian processes with a Matern kernel. And so, as I said, to get a sample from a Gaussian process, you just need to solve this partial differential equation by finding an inverse to this operator, i.e. solve for f. So how do you solve for f? You bring this over to the right-hand side. It's not entirely clear how you do that when f is a function, but if f is a vector, it's easy because you just need to, this becomes a matrix and you just invert the matrix by, for example, Cholesky decomposition or a different algorithm. And so the idea is that we have a Laplacian from the graph, which is defined by the adjacency matrix, which is W, and a diagonal degree matrix. And the degree is, if I've got a point, how many other points is this node connected to? And the weight matrix is for every ij index of points, the ijth value of this matrix defines an edge. If that element in the matrix, the ijth element is non-zero, there is an edge there, and its value in W, the element of W, is the weight. And so then the graph Laplacian is the degree minus the weighted adjacency matrix. And it looks something like this. Here is an example from David Mackay's lecture called The Humble Gaussian Distribution. It's from around 2006, and there's a talk that goes with this that I'd recommend watching if you can find it on YouTube. And if you have some masses in a heat bath, so it's vibrating away, and then the displacements of these springs are y, the outputs, then the system has an energy, and it's the energy that's defined by the displacements and the spring constants, how stiff the springs are. And then if you write this energy down, it's a quadratic function of the displacements, because energy is work done is force times distance, something along those lines. And you can write that down in terms of a matrix applied to these data. And then that matrix turns out to be really related to the graph Laplacian. So you can see that this is the weight of the adjacency matrix. This is like the degree. So the so that's what the graph Laplacian looks like. It's sparse for a sparse graph when you haven't got that many edges. Do this stochastic partial differential equation, and the way we do that is that we introduce a notion of functional calculus, and that's a fancy way of saying that let's do an eigen decomposition on this Laplacian matrix, and then that would be a eigenvalue matrix with some basis eigenvector matrix U, and that in order to apply this operator, which was on the left-hand side of the stochastic partial differential equation, then we'd only operate on those eigenvalues. And so if you want to go into the details of the maths, then I'd recommend going to the parent paper, Return Gaussian Processes on Manifolds, which explains it in more detail. A key point here is that from this stochastic differential equation to here, we've dropped D because the dimension doesn't make sense anymore. A graph doesn't have a dimension because a dimension is a dimension of Euclidean space. So the notion of dimensionality doesn't make sense anymore, and it's not needed. And so this is an example of prior draws from the Gaussian process, and the values depend on the edges and how connected the node is to other values. So now that we've got the stochastic differential equation, how do we solve it? By bringing this operator, which is now a matrix, over to the right-hand side, and then that becomes the inverse of that matrix, which is then the covariance matrix. And then we can use multivariate Gaussians in the normal way, condition on data, and get predictions. So for sparse graphs, the Laplacian is sparse, which makes the scaling easier to train. But if it's not sparse, then we might have a problem. This figure is showing some convergence between the graph Laplacian and then the Matern kernel, so the graph kernel, and then the Matern kernel on a sphere. And the only reason that it converges in the way that it does is because we've specified weights that depend on the distance on this sphere, the geodesic distance. But if we didn't do that, we carefully assign the weights to these edges. One idea is, well, how do you know what the weights of the edges should be? In the road example, it was the inverse distance between the measurement locations. But in this example, it's certainly not the inverse distance between points in the sphere. It's something else. And how do they know that?
This is actually my thinking when I wrote this paper, is that there's a specific area of graph structured data, which is approximating continuous manifolds. Mm-hmm. Like usually it's physical problems that have to do with modeling objects or something like that. Mm-hmm. And in those cases, I think this method makes a lot more sense, because there is like the underlying math here is that you're approximating a manifold with a graph. Mm-hmm. And so in those cases, this would make sense, but there's other cases, like probably this road problem, where there's like the manifold that you're approximating might be like completely not smooth, and then you need some kind of other distance metric that you use. So anyway, yeah, I was thinking this is probably a method that itself more to these physical problems that you approximate with graphs than maybe like human systems and stuff like that.
Yeah. So I guess like, yeah, so there's like definitely a sphere here that we're trying to approximate the kernel on, but in the road example, or it's not a sphere, it's just a graph. And so it's not, we're not trying to show kind of convergence between the different ones, but we just want something that works well.
Yeah,
I guess. And so I guess that's what they're trying to get at. Here is an example. It might not be the most realistic example. For one, it's a snapshot in time and traffic flow varies over time. But I think they use this example as something to like stimulate the imagination of practitioners, is what they say in the paper. And it's an example where you definitely get better predictive performance because you take into account like the structure of the graph. Across the road, the traffic flow is not the same. And so we wanted to model that. And then the second example is a citation network, which doesn't have weights on the edges. So we've got no problem there. And it's a citation graph for Quora, citation network. And the colors represent the topic, the scientific topic, of which there are 7. And the edges represent if this paper, this node, has cited this other paper, this other node. And so that they use the training set to find the Graph-Laplacian, put it through the operator, which defines the partial differential equation, invert that precision into a covariance, and use that to make predictions. And they get 80% of the test set correct. So 80% of the predictions predicted the correct scientific topic that paper was. So that's pretty cool.
One question I had is for both of these, they used one of the kernels that they tested against was this inverse cosine kernel. How does it calculate distances in that case? Like, how does it use the graph? Or yeah, I guess it's a poor question.
And yeah, I'm not sure.
Okay.
Yeah, I don't know. They don't give the definition of the inverse cosine kernel.
I was thinking, why didn't they? Maybe because they were like, it's just going to perform really poorly. But I was thinking, why don't they just also have one of for the traffic using Euclidean a kernel based on Euclidean distance, just to show
how that much better it works. Yeah, that would be a good comparison to make, especially as they're comparing like their kernel, the Matern kernel, and the diffusion kernel to these other kernels, and like it wouldn't be any extra work really to include Euclidean kernel. But then again, in the citation example, there is no notion of distance whatsoever. It's just, is this paper cited by this paper? Yes or no. So I guess it wouldn't work. And for that one, it would be empty, but then they've got empty things here. So yeah. But yeah, I think that's pretty much it. We could, if we've got time, go over the variational inference stuff. I could attempt to explain this.
One quick question about the results is the results for maybe just talking about the random walk kernel, the inverse cosine. Anyway, the random walk kernel or the inverse cosine is like, they're basically saying that they're comparable to each other. Like you don't see a massive improvement in performance from using the Matern kernel or the diffusion kernel. Is it in those cases, is it that the sparsity of the matrix allows the computation to be a lot quicker, and that's why you would use this method? Or are they just showing that this is another method that you might want to employ?
I think it's to do with the sparsity of the matrix, but it's not to do with scaling. of compute. It's to do with the fact that if you have a sparse matrix, then a Matern kernel performs well because sparsity in the precision matrix implies not smooth. And so if Matern is the not smooth version of this really, really smooth diffusion kernel, then it's just saying that it's well, these functions are well, this interpolation is well modeled by a non-smooth function equally as well as it's modeled by a smooth function. Because I guess the smooth function can capture everything that like the non-smooth function could capture. And that's because these graphs that we're dealing with are sparse, or that could be one idea as to why they both work as well as each other, I think. Any questions in the chat? We can end it there if you want.
Okay. Okay, let's stop recording.